So, good morning and a very warm welcome to our distinguished speakers and our wonderful PMRF scholars. I hope you had a wonderful day one of the symposium. Now, welcome to day of two of the symposium, and I hope everyone had a restful evening. So, today we'll start our session with another very exciting plenary talk lined up. So, our first inspiring talk will be given by none other than Professor T. Pradeep. I would like to welcome him up onto the dais. So, welcome, sir. Stage is yours.
Okay. So this is a very nice thing without any introduction and all that. Please go ahead. Yeah.
So while the presentation is getting ready, I would like to introduce the audience to Professor Pradeep. Professor T. Pradeep is an institute professor at the Indian Institute of Madras, Chennai. He is the Deepak Parekh Institute Chair Professor and is also a professor of chemistry. He studied at the University of Calicut, Indian Institute of Science, UC Berkeley, and Purdue. His research interests are in molecular and nanoscale materials. He is the author of over 550 scientific papers in journals and is an inventor of over 100 issued patents. He is involved in the development of affordable technologies for drinking water purification, and some of them have been commercialized as well. His pesticide removal technology has reached about 10 million people. His arsenic removal technology, approved for national implementation, is delivering arsenic free water to about 1.3 million people every day. Along with his associates, he has incubated 7 companies, and 3 of them have have production units. He is the recipient of several awards, including the Santi Swarup
Fantastic. Thank you
Bhatnagar
very much.
Prize, BM Birla Science Prize, National Award for Nanoscience and Nanotechnology, India Nanotech Innovation Award, JC Bose National Fellowship, and National Water Award as well. He has won the World Academy of Sciences Prize in Chemistry for the year 2019. He was conferred the Civilian Award Padma Shri in 2020. He is also recipient of the Nikki Asia Prize, Prince Sultan bin Abdulaziz International Prize for Water, Win Future Prize, and ENI Award. Recently, he has also won the International Excellence Award for Karlsruhe Institute of Technology, Germany, and the Fellowship of Schroff Foundation. He is also the author of the introductory textbook Nano, The Essentials by McGraw-Hill, and is an author of the monograph Nanofluids, Wiley Interscience, and an advanced textbook, a textbook of nanoscience and technology, McGraw-Hill. He is also on the editorial boards of journals such as ACS Nano, Chemistry of the Materials, Analytical Chemistry, Chemical Communications, Nanoscale, Environmental Science and Technology, JPC Letters, etc., and was an associate editor of ACS Sustainable Resource Management. He has authored popular science books in English and Malayalam and is a recipient of Kerala Sahitya Academy Award for Knowledge in Literature. He has received the Lifetime Achievement Research Award of IIT Madras and Distinguished Alumnus Award of IISc. As a part of philanthropy, he supports a school in his village where 500 students are on rolls. Please join me in welcoming Mr. Professor Pradeep on the stage.
Thank you. Thank you. It's always a pleasure to come and speak about one's own work when students doing similar science are in the audience. This work was done by a student who is not a PMRF. Of course, there are several students of mine uh, who have received PMRF, and It's a great encouragement for students. Uh, is difficult to refuse. He was my classmate, uh, batchmate at Indian Institute of Science. So I thought it is important to come here. But then, after accepting it, he told me, well, your time is only 30 minutes. 15 minutes you have to give to students to ask questions. So then I decided to talk about one paper and not the regular talk that I do on many papers together. So just one paper. And I thought it is important because, as I said previously, it's about one student doing something intensely for some time, was just graduated, and she is a postdoctoral fellow. So that uh, said, the topic I will be talking about is on water microdroplets. Water is the mother of solvents, the mother of all liquids. And Professor D. Balasubramanian, sitting here, of course, would say that it is a mother of biology. But it is mother of all liquids. And today we are discovering something new in droplets of that liquid. And that has taken me to a paper. So if I were to tell you about such droplets, these droplets are matter in confinement. Matter in confinement of this kind, like bubbles, are everywhere. I did not see a rainbow today, but here you see rainbows all the time. Well, you can see interesting colors. But matter in confinement is important for sustainability. Some of us confine electrons in matter. And you also you can confine molecules in regions of space. We call them clusters. Or we can confine atoms. So all of these are exciting from the point of view of catalysis, carbon capture, energy storage, and what have you. But this is also becoming interesting in droplets. So I published a paper last year, and this was about droplets of water breaking sand to nanoparticles. And what is this thing about? And that, in order to tell you that in some detail, I should tell you why this is exciting. You know, matter like this, big rocks, this is giant rock in the US. Giant rock is about 22 meters tall. So meters tall rocks become millimeter scale sand in millennia. And that is the sand that is there. And it is like, well, let's say if you take a micrometer scale particle, becoming a nanometer scale particle is like meter scale particle becoming millimeter. Both are orders of 3. Well, it is a factor of 1,000. Now, this pointer is not moving as efficiently as I would like. Now, this kind of a thing is making soil, making particles of soil. The most important ingredient of such soil, if you want to do agriculture, is nanoscale particles. With such nanoscale particles, we grow rice. 15% of rice stem is silica. And people know that by improved silica, you can enhance agriculture. So this is all very exciting. So to tell you more about this, I should talk about some functional nanomaterials that we make with droplets. This is not moving. I'll stand here. So if you take micro droplets, these are micron scale particles of liquids. So these microns could be 10, 20, 30 microns. So with these liquid droplets, we made nanoparticles long ago because these are highly reducing, we realized at some point in time. You can also make, instead of zero-dimensional nanoparticles on the left side, you can make one-dimensional particles by assembling particles together. You can make two-dimensional sheets. You can make three-dimensional objects. Many of these have been subjects of research in our group for a long time. If you take two different types of particles, like a spherical particle and a rod-like particle, in a droplet, these particles phase separate. On the one side, you have drops, the rods, and on one other side, we have spherical particles. You can see them with microscopy. If you come to our laboratory, you can see individual particles of this kind. And these particles that you see can be imaged, well, in a droplet can be imaged with dark field microscopy. So there can be many things exciting. I was also asking this question, is it possible that one can transform particles in droplets? You know, many of you may be making nanoparticles. In solution phase, when you make nanoparticles, they are of different types, like these. These are called polydispersed particles, on image 1 that you see, image I. And these polydispersed particles, if you put them in the form of a suspension and then spray them by a technique called electrospray, all that you do is, in that suspension, you apply a potential and you draw the droplets formed at the tip. They produce something called a Taylor cone. You draw these droplets to a surface, which is an indium tin oxide surface, ITO it is called, and you image them. And you image on the right side, what you see is that the polydispersed particles become monodispersed. So that was the time when Spurti in my group, I wanted her to explore something new. Well, here if you have hundreds of, let us say, chemical bonds which make a particle, these chemical bonds are breaking and reforming into smaller scale particles. I asked her, what is the limit that of breakage that droplets can do? Can we break a rock? So this is what I asked her. Of course, Purti spent quite some time on this. What is the rock that you should break? Well, you should probably choose the right rock. I chose, well, ask this question, what is this rock that is most exciting? You take silica, because silica is mother of soil. And silica in great detail is nothing but quartz. Of course, there can be some iron and all that, some silicates, but mostly it is quartz. This particle that you see is quartz. So having decided that you would ask this question, can quartz be broken in droplets? It was quite easy then. I asked my dear friend Manu Santhanam, he is a civil engineer, structural engineer, give me that sand that you study. So Manu studies this kind of sand. It's the Ennur river sand. It's a standard river sand. So you must have some good friends in civil engineering. So then, of course, it has to be made into this is millimeter scale sand. This is used as a standard for Young's modulus for concrete. So you grind it. You grind it to make micron scale particles because I want to put these micron scale particles into micro droplets. And that is the optical microscopic image. You suspend these particles in water, and then you connect a wire, a platinum wire, to apply an electric potential to this, electrical potential. And then you put an ITO plate or any conducting plate. You can also put a transmission electron microscopic grid at a distance L, and you apply 4 kV. At 4 kV, or just below 4 kV, this liquid starts spraying. So this spray is called electrospray. It's a very well-known thing. An electrospray won a Nobel Prize. This is a person called Fenn. He used this to fly elephants. Elephants that he talked about are proteins. So heavy elephants could be flown in electrosprays, and then those heavy elephants would be measured by mass spectrometry, and their masses were determined. So here we are flying these particles, but then these particles are now encased in micro droplets. And these micro droplets are charged. So in image B, you see the river sand that Manu gave me. C is the ground particles. D is what we saw on this TEM grid, only nanoparticles. Take one particle and expand it, you see the lattice plane, the particular was 110 of quartz. Okay, quartz is down. So we went on doing this for months together. And I was asking Spurti, what is the limit, well, of this breakage? It's, of course, is it only quartz? Can you go and do other minerals? At that point in time, the source of mineral supply changed. I had a friend who runs a gemology institute in Chennai. His name is Sultan. Sultan gave me some ruby. Ruby, as you know, is chromium doped aluminum. So you grind it, and that is image B. That also makes nanoparticles image C. What about natural alumina, corundum? We did that. How about synthetic alumina, which is image D, and that is microscale particles, image E, and that also becomes nanoparticles. Fantastic. So we can break many, many minerals, and we have now a collection of 142 minerals from this gemology institute. So you can do all of those. But they may not be, all of them may not be so fascinating. Silica was fascinating. You change potentials. So you see from A, B, C, and E, you see different potentials, and you can change the shape, you can change the morphology. All of these are fascinating too. But if I were to tell a materials chemist like Murthy or materials scientist like Murthy, telling him that, well, we can break these into nanoparticles, he would like a material science technique. And the material science technique for such materials is powder X-ray diffraction. So on the extreme right that you see, silica in JCPDS, in this particular 2 theta window, you have 2 peaks. Silica before electrospray and silica after electrospray, you see the same silica. The only difference is the size has increased, the width has increased. So this is fascinating, but I couldn't publish this because this is so exciting, but no one would believe it. How do I convince people? So I walked around. This one, the B, the top one is 16 nanometers. Yes. And the original one that I saw was 5 nanometers. This one is 5 nanometer is the scale of the inset that you see. It's about 10 nanometers, 10, 15 nanometers particle that you see. Okay. So one day in one meeting, I met Umesh Wagmare. I asked Umesh is a professor in JNCASR. He was the president of our Bangalore Academy. Professor Balasubramanian was also its president some years ago. So I asked Umesh, what is happening? Can you ask your students to work on one of these questions that I was sort of keeping in mind? In a droplet, can you see whether mineral breakage is feasible? How do I do that? I asked Umesh, is it possible for you to ask or calculate the cleavage energy and ask what is the change in cleavage energy as a function of the size of the particle? So he computed that. In image B that you see, the energy E is the cleavage energy. And he is asking this question, what is this dependence of the cleavage energy as a function of size? In the red one that you see, the cleavage energy is lower for scale piece of matter than a bulk. So cleavage energy reduces with size. There are more details which I'm not getting into. But is this the, of course, cleavage is easier. But is cleavage is the only way to break particles? Not really. If you take a particle like this, you can also undergo slip. And you can ask this question, what is the energy required for such slip? So this is, a slip is nothing but a stacking fault. A series of stacking faults that you do atom by atom by atom, you keep slipping, slipping the material. And we found that slippage is possible, but you can ask this question in a particle, in a droplet, the droplet which is charged, there is a high electric field at the surface of the droplet, separating the droplet from the air or the medium. And this electric field might be acting on these particles that is inside. So we ask this question, what is the effect of electric field? And we also asked additional questions. In such a droplet, many of our friends have shown that water can produce protons. So what is the effect of such hydrogen atoms or ions? So in this, what is shown here, the table, stacking fault energy is calculated. I told you there is a stacking fault is what you are inducing. What happens when there is protons present? When there are more protons present? When there is electric field present? So you see that the stacking fault energy along particular direction, you look at the last column, it becomes minus 1.2 because it becomes more facile. What this calculation showed was that you can induce stacking fault, but in presence of protons, the stacking fault energy reduces. In presence of electric field, even more reduces. Today we understand that rock undergoes proton induced slip and breaks. And that is so fascinating. So, when such proton induced slip occurs, the protons can get attached to SiO and it becomes SiOH. And as a result, silicate pieces can come out into the solution. Did we detect silicate pieces? So I'm showing you some silicate pieces in that extreme end, and I detect them. So this is a mass spec which shows very many silicate pieces in image A, and image B or spectrum B, you see a comparison of the spectrum of sodium silicate. So you see silicate you can buy from Aldrich or any chemicals manufacturing company, and you can do mass spectrometry slash mass spectrometry called tandem mass spectrometry. So we understand roughly how this occurs. But if you take a droplet without the silica inside, I said that it can have protons on the surface. If this acidic droplet falls on some silica, what would happen? We studied that and we found that on the left side is particles of silica. Right side, when you go on putting a lot of these droplets over a long period, you do see some corrosion, but they don't make nanoparticles or convert all of them to nanoparticles as we saw. So, what we said was that in droplets, which are all charged, having reactive species like H3O plus or OH dot, hydrogen peroxide, hydroxyl radicals, all of these, they're all interacting with this rock. But then, as this droplet is moving in space, its size is decreasing, and the charges are repelling the droplet, repelling against each other, and the surface tension cannot hold this droplet, and the droplet breaks. So that is called the Coulomb fission that occurs. At that time, a daughter droplet gets formed. Along with that, the proton-induced slip occurs, and then tiny nanoparticles are formed, and they are thrown out. Of course, this process continues and continues. More and more of these nanoparticles get formed. This proton-induced slip is fascinating, but that by itself may not be adequate to give enough activation for these rocks to break. So what would be happening? Well, we go back and ask this question. What did people like Raleigh think about Coulomb breakdown? So what we can today see, well, although Raleigh did not talk about this, so when a droplet is breaking apart, there are internal pressure fluctuations. And these pressure fluctuations can be as large as 200 megapascals. And these intense pressure fluctuations might be triggering the particles to break, which are then facilitated further by the protons present. In addition, many, many other things can happen. So if a droplet is falling down, you can have charges that are present, as I just told you, but an analyte that is inside the droplet can get partitioned between the surface and the bulk. Analyte can get concentrated because of the solvent evaporation. There can be physical confinement because of surfactancy. A whole lot of phenomena can occur, and people have written about this. They may not be very important in our context, but all of them are relevant. So accompanying this article, Professor Graham Cooks and Dylan Holden wrote a perspective. And they said that this can be very fascinating from many other perspectives. For example, The droplets which are breaking these minerals, the mineral surfaces are naked. And these naked surfaces are very reactive. They are catalytically active. So if there are some molecules present, there might be new chemical bonds being cooked in the droplets, which may be of interest to biology. So lots of such possibilities. I just mentioned one of them. But there can be many exciting fundamental questions. How would a droplet break? So if you do this experiment in such a way that as this droplet is moving, if you are in a position to capture these droplets in between, you might be seeing situations wherein a rock is just beginning to break. So here is one such picture. We are exploring this today. This is unpublished. Anubhav Mahapatra, another student, is pursuing this in great detail. Spurti, when she was about to leave, she asked this question, can this be taken further to materials like molybdenum sulfide? So here is molybdenum sulfide, two-dimensional sheet becoming nanoparticles. You can then ask this question, can graphene become that? Yes, graphene will become that. So today, many materials are being studied, and they're all explored with spectroscopy, microscopy, and all that. Why are we doing this? You know, some of you sitting in this audience will know that I have this interest in clean water. Create advanced materials, porous materials, and make clean water. And this activity today has become very big. Today, these products are there across the country. So that blue box that is sitting there under the water tank is a water treatment unit that came out of our research. So it has reached several millions of people in supplying clean water to people. There are many, many things that we are doing in our laboratory, translating new research to products. It's important for you. And using such technologies, we are monitoring water quality for the country. So if you look at it from this perspective, what is the science telling us? This science is telling us that droplets could break particles, right? Droplets could break particles to much smaller things. This is what is weathering is. Weathering, for years, we thought that this is happening by many, many means, but droplets were not in one of those parameters in the equation. So when droplets are falling down in the form of rain or whatever, they are charged. By the way, they are charged because of sodium chloride mostly. And they are charged because of triboelectricity. And when they fall back or fall on the surface, they pick up particles and they bounce back. They have charges and they undergo all of these processes. And maybe they are producing active silica. Why is active silica important? You know, if you think about a city like this, which is producing millions or hundreds of millions of liters of sewage water, you can recycle. Without recycling, you can't live. This planet has no future without recycling. But that water, recycled water, could one day be used to convert sand to active particles. These active particles could be porous, as I just told you in one of those images. They are anisotropic. They could include urea and such other fertilizers. So you are talking about augmented soil. This could enhance agriculture. So we did this experiment in the laboratory. We can do that more, and we understand we have not gone all the way to expanding into meter scale, meter square areas of germination and agriculture, but it is very much possible. This water itself is fascinating. Today in our laboratory, we have a microscope called a new microscope that has been installed, a cryo-electron microscope. So in cryo-electron microscopy, we ask this question, can water include molecules? and create clathrate hydrates. And using a Swarna Jayanti grant long ago, I built an instrument with which ice can be deposited on surfaces. And we today know if you put methane molecules on ice, this will form clathrate hydrates even at 10 Kelvin. So what it means is that in astrochemical environment, where there are molecules like these, water is present, and there are particles of dust that is present, and it can form clathrate hydrates in those environments, and we showed that. I'll take two more slides and then close this. So we have this, and we study this with spectroscopy. And when a molecule that is caged inside, its vibration is very different. We study this in great detail, but can I see it with microscopy? Today, with cryogenic electron microscopy, we can see ice. And the image B that you see is cubic ice. I'm seeing the lattice point of water. And today, I can observe it. It's also possible that tiny crystals of clathrates can be made, and these clathrates are solved by electron diffraction. Fascinating science is being born today around you by students like you in laboratories. But some of these science, of course, have tremendous importance for the water science that I just told you about. For that, we have built the International Center for Water. People can come and build technologies. Anyone can come and build technologies. But for water to be there for everyone, we need to have water data for the planet. So with that objective, we have introduced a course at IIT Madras called People's Water Data. Students take the course, but at the end of the course, studying about water, they go to field and measure water quality. So these are water quality data collected by students across the world just beginning of this course. Only 3 semesters are over. These are appearing like single data points, but they are not. They're 10,000 data points. Each one of these points, if you expand, you get data like this. And today, these data are being used to build water quality of the planet. Many other exciting science that goes on. And one thing is clusters. And today, students like you, another PMRF this time, has published this paper making new clusters. So in conclusion, I would say that natural minerals break spontaneously in charged water microdroplets. They occur today only in water. I told you that fascinating fluid only in water. We have never seen this happening in any other solvent. Studies of a variety of materials have shown that this is universal. It occurs due to proton-induced slip. Detailed investigations are going on right now. And even how this droplet is breaking in real time. And how about building a company on this to break sand? So we are in that process. So my science is done by a lot of people across the world. Many other activities happen with the support of Science and Technology and Institute of Eminence, with a lot of funding from different agencies. The student who did this experiment is Purti. A postdoc now at Purdue University. Many of these students have built companies. Today the lab is very big. Today this is the current group. The work that I mentioned to you was done with Umesh Murray, a fantastic scientist. He's a computational materials scientist of the highest kind that we can have in the country. And this is Indian Institute of Technology, where we live with wildlife and a lot of students. Thank you very much.
Thank you so much, sir, for that fascinating talk.
Now I would request the audience to engage in a question and answer session with Sir.
Thank you.
I learned a lot. Just I, as a material science by scientist by nature, I will call myself scientist now. I will say, uh, I have a feeling that as the size reduces, the cleavage energy or the slip energy should increase. But as per your talk, I got that you're claiming that it should decrease as the size decreases. So there, here I feel I'm not very sure how it happened.
Okay, sure.
And
So, all these energies are a sum of surface energies. Every material, sum of surface energies. So, if you create a two-dimensional nanoscale object from in comparison to the bulk, it has more surface. So, all that you have introduced in cleavage is creating additional two surfaces. The energy required for creating such surfaces will be smaller when the overall size of the object is smaller, which has more component of surface energy. Think
uh,
about it.
can I give you another whatever I can
Yeah, sure.
imagine in this way? As the particle size gets smaller, the surface tension will increase.
Yeah.
And as the silica particles are also negative, and you are using a proton charged sphere of water, that's the surface energy will try to pull down those particles apart. So that can be a major factor. And as we can see, your the simulation first principle calculations, the bulk is having high energy. That I agree, but it can also be, as we can see from the images, it was a few particle system. It was not a bulk, and what is the surface differential was not there. They are taking only us 100 million out, some million atoms, right? So I feel there can be a more to explore in that side rather than just saying that surface energy will be playing more role in the slip. Because for the slip also, as you go into nanoparticle size, I feel the surface interactions will try to maintain the size rather than being forcing them apart. So
We can certainly discuss this. I think it will take a little further for
yeah,
me
sir,
to
thank
convince you that this is very important. Now, it is also important to look at the overall energy. Okay, I will just
you.
leave that thought with you.
Okay,
It is
sir.
not just what is happening is the overall energy of the droplet with these particles together, the additional energy required to create the separated particles embedded in the liquid, that difference is what you have to reduce.
Okay, sir.
Okay, so overall it is a matter of how new surfaces are being formed, how these new surfaces create new chemical bonds. In the case of silica, all the new chemical bonds are very strong because all of these are SiO bonds, and SiO bonds in comparison to H2O bonds, this is what we need to compare. Overall energy is what we need to compare, and that is what we have done. Okay,
Thank you very much, sir.
thank you.
Distance from the collector to the charge. So,
Yes,
did that have any impact on reducing the particle size, or it is?
absolutely,
Yeah.
absolutely. So if you, there is a critical L at which this begins to occur. And as I said, you change the electric field, you change the kind of an anisotropy or particle size and shape and distribution changes. This is also a function of L. And so essentially the droplet, how much of electric field it experiences is a function of L. And the size of this droplets change also in that process. It takes more time for when there is more length, it's more time for this droplet to flow or to travel, and that changes the critical droplet diameter. So several parameters are involved. I told you that one has to optimize this. And at that particular distance of 1.5 centimeters and 4 kilovolts of potential for this kind of droplet, the interesting phenomenon occurs. But we have then studied many different kinds of droplet dimensions with varying distances, but it can be generalized today.
So just like follow, like so collision energy has like there is any impact on collision energy? Or there is,
It does not occur upon collision. This
right.
process, of course, collision occurs, but the breakage occurs even before that. So what is falling down is milk powder.
Right.
Okay, so breakage has occurred and then it falls down.
Thank
There is coming.
Very interesting, sir. So actually, I am working on microdroplet chemistry also. So
Fantastic.
myself Tirupati. So just for my knowing that you are spray with the charged microdroplet, but a neutral droplet. The neutral droplet you play that is also more nearer to the nature because I calculate the current. So if the current you see the 4.5 kilovolt, it's load the 64,000 proton on the droplets. So, but in the neutral droplet, the protons is only 5 6. So, is it for neutral droplet will happen, or is for the charged droplet phenomena?
Okay, so that's a subject by itself. That is, without charging, what happens? At a critical size, any material, water droplet will begin to behave differently. At that point in time, you may not be in a position to put 10 micrometer size particles inside. 10 micrometer size silica particles, nothing will happen with neutral water. Charged water, only this phenomenon occurs. But if you reduce the particle size smaller or droplet size smaller, and you put a smaller silica particle inside, new phenomena could occur we have not studied. Now, is it possible that without applied electric potential, can you charge water? We can charge it by putting salt. It's also possible that triboelectric charging occurs. So we have seen that you can generate charges on neutral water droplets by allowing them to pass through air for extended periods, and that charge can be enhanced by salt as well. Under such conditions, will silica break into nanoparticles? We have not explored it. Okay. Now, in nature, many different kinds of charging can occur. You can have charging as a result of lightning, and many such things can produce lots of charges, megawatts of charges, gigawatts of charges. You have a question here. Okay.
Thank you for the great talk, sir. Sir, actually, sir, as this is top-down approach for of the nanoparticle synthesis, so how is it different from the bottom up in terms of like in the bottom up we go for this nucleation kind of thing. So first cluster forms and then the nanoparticle. So how is it different from that? And then, sir, I'm working on this micro nanoplastics. So these small micro polystyrene beads which is being synthesized, how that is different from the synthesis of say gold nanoparticle. And the last one that I want to ask, like in this one, you just use the water droplet and the silica, right? And the electric field, electricity. Uh, Now, if say surfactant or some salts are there along with the water in the solution, how it will different the final morphology of the formed particles, whether there will be some change.
Well, the last one, you can always add for surfactants. You can add reagents. You can change the resulting particles and all that. Coming to your first thing, how is it different from top down and bottom up? Ours is top down, this particular approach. Now, top down approaches in general are said to be uncontrollable, really, in the sense that you don't have that extreme chemical control, shape control, size control. So today in our laboratory, we make atom precise nanoparticles, meaning 25 atom particle versus 29 atom particle. We do synthesize this chemically. To that extent, the, the top down approach is not versatile enough. Will this become at one point in time that there are people who do this kinds of extremely uniform particles or nanoparticles, even with top down in solution? So bottom up is not the only way, is all that I wanted to say. Coming to your other kinds of materials, polystyrene and such other things, the phenomenon that I just talked about is universal. And it is possible that one can create particles of polymers, particles of any object by methodologies of this kind.
Yes, thank you.
Thank you. Thank you.
Thank you so much, sir, for taking the questions. Now, I would request Professor Dipankar Chaudhuri, PMRF Nodal Coordinator from the Broad Area Civil Engineering, IIT Bombay, to kindly come up on the stage for felicitating Professor Pradeep. So, up next, we have our esteemed plenary speaker, Professor D. Balasubramaniam from LV Prasad Eye Institute. Before we invite him to the stage, here is a brief introduction about his remarkable achievements. Professor D. Balasubramaniam is a distinguished scientist and former director of the research at the LV Prasad Eye Institute, Hyderabad. He has made pioneering contributions in biochemistry, molecular biology, and ophthalmology, particularly in the study of cataracts and corneal disorders. He served as a professor at the University of Hyderabad before joining LV Prasad Eye Institute, where he led transformative research in eye diseases and vision sciences. His work on protein aggregation, lens biology, and eye genetics has significantly advanced treatments for blindness and visual impairments. Professor Bala Subramaniam has played a key role in developing affordable eye care solutions impacting millions in India and beyond. In recognition of his achievements, he was honored with the Padma Shri by the Government of India in 2002 and has received numerous other prestigious awards. Notable among them are Shanti Swarup Bhatnagar Prize, Kalinga Prize from UNESCO, and the Third World Academy of Sciences Award, and the Chevalier d'Or des National du Mérite from the President of France. Professor Balasubramaniam is a visionary scientist and mentor who continues to inspire advancements in biomedical research and public health, ensuring access to quality healthcare for all. Let's give him a warm welcome as he takes the stage.
Thank you, Pradeep, for an outstanding lecture. And of course, I have known him for the past two decades or so. When I was at IIT Kanpur, and I was a member of the Academic Council of IIT Madras. Today, however, I'm not going to talk about any technology at all. The reason for that is I was told this is the Prime Minister's Research Fellow meeting. You see that? And so there must be a lot of research fellows who might be interested in looking at that. I'm particularly delighted that out of that, there are several girls who are sitting here. And that's important because remember, just about 10, 15 days ago, we had the World Women's Day. And in fact, I was asked by Professor Ajay Sood, who is the Prime Minister's scientific advisor, आप वहाँ जाके ये बात करिए. You speak particularly about women in. Incidentally, Pradeep, you showed me the picture of one girl. It was a girl. All that about water becoming droplets, becoming nanoparticles, and making deserts like Pilani and so on to green is largely because the kind of work that one girl student or postdoc has done. So I thought I'll do that. As she announced, my work has largely been in the area of molecular biology and genetics and biochemistry of vision. And I moved from being a regular molecular biochemist into one in the eye, largely because from the University of Hyderabad, where I moved, to CCMB, the Center for Cellular Molecular Biology, I was told that this will be interesting to try and look at vision sciences. And so once I retired from there, I moved over to the LV Prasada Institute. And interestingly, you would notice the LVPEI, as it is called, which offers a cure for blindness, essentially for cornea and the retina. The cornea is the front of the eye. It's a lens. It focuses on to the entire eye. And we found a method to artificially produce using molecular pharmacologies and so on to focus these so that corneal blindness is one that need not be at all worried about. To this date, it's been possible for us to produce 50,000 corneal surgeries just using donor corneas. So I think this is the kind of a thing that, and even here, where does most of this corneal blindness occur? Not as much in cities as in urban poor, and certainly in the rural areas and so on. So I'll talk about that when I come over here next. If Professor Murthy calls me, and but today I want to focus on the role of women who've been making remarkable advances in health, wealth, and happiness among people. As I said, International Women's Day was celebrated on March 8, 2025. I was delighted to learn that you people at IIT Hyderabad, this is particularly interesting. They have as much as 30 women faculty. This is the latest figure is 38. And this is something very interesting because compare this with the other IITs 10, 20, 25, and so on, including IIT Madras. So it's interesting that we have and also enriching that IIT Hyderabad has been leading the role in this. The United Nations Development Program UNDP in its Gender Social Norms Index or GSNI quantifies the biases against women, capturing people's attitude and women's roles in four dimensions: political, educational, economic, and physical integrity. It's the last two dimensions that men leave for women. Of the 8 billion people across the world, 45% are women. Men claim that a woman's job is to maintain houses, homes, make food, make and care for babies, while men bring home the income. In many developing countries across the world, women do not even go to school. It's here that I think our state, Telangana, has been very good. And that education from nursery all the way up to the class 8 or class 10 is free for all children in government schools. But in spite of that, we still have women who work as farm laborers and housemaids. The educational dimension should therefore not be given a miss. India is usually dubbed as a developing nation. It has shown the way ahead in inclusive politics. Since the last 2 decades, India has offered free education to all children, poor, rich, rural, urban, and all the way up to high schools in government schools. And about 12 crores every year of rural children, women, are given this. But when we go to higher education at the graduate, postgraduate, and PhD level, largely it is the paternal pressure that that lets most women opt for essentially nursing and medicine and so on. Whereas the boys usually are asked to go over for BSc and MSc degrees in computer science, biotechnology, and, and digital tech, etc., at the PhD level. But at most STEM, science, technology, engineering, and mathematics, institutes across the country, unfortunately, only 20% of the students are women. Also, among the faculty members in STEM, many CSIR labs, where I come from, All India Institute of Medical Sciences, ICERs, IIT managements, and so on, only 20% of women. It's here that I commend IIT Hyderabad. IIT Hyderabad, about 38 women in the faculty in STEM. In STEM, not just in literature or things of that kind. In bioengineering, biofuels, molecular biology, mathematics, and even in humanities and social sciences. It's important. An institute of technology should have social aspects and humanities and social sciences. When I was teaching at IIT Kanpur, we had a remarkable lady who was called by the director to become a professor, Usha. Okay. And Usha would give a lecture essentially in terms of what is humanities like, what are economics, why did people get the Nobel Prize for Peace. And you notice many such are not known to many graduate students and so on. And Usha Kumar would actually give these certificates. Take there's an optional course, you can take that and so on. That transformed a variety of people, Mahindras, okay, who now are one of the biggest manufacturing companies in the country. One of the students there was one of the Mahindras and said, I think we need to do something about this. And we will do that soon. And therefore, I'm happy. IIT Hyderabad also has people in mathematics, humanities, and social sciences. I personally know one Haripriya Narasimhan. She has a collaborative program in the area of digital health ecosystems, but she also has written a book on Tamil Brahmins. I'm one. Okay. And I have to read that and see, oh, is this what, how did this entire thing happen and so on. This is important since one cannot just be professional, but should also have interest in liberal arts, literature, music, and so on. Here again, this institute is commendable. And in fact, IIT Delhi and Delhi University also, at that time, as early as in the 1980s, one professor, Kiran Seth, there started. He wanted to know to certainly inculcate the classical music programs, art, dance, and so on. Speak Mackay stands for, as you know, what it is. Okay, Society for the Promotion of Cultural Arts and Science among youth. On this score, there are also a lot of women who are entrepreneurs in India. Many of them are involved in the entertainment business, advertising, film industry, fabrics. Again, notice Telangana and Andhra Pradesh are particularly important in the kind of fabrics and silk that they make in here. But there are quite a few women in science and technology degrees who have established biotechnology and drug companies that make useful and profitable products. Many of you have heard of Professor Kiran Majumdar Shah. Any other girls? You know the name Kiran Majumdar Shah? She's a Gujarati lady who went over to get further training from Australia and in London and came back and started, along with her husband, Shaw, something called Biocon. It's settled in Bangalore and it makes a variety of drugs, molecules, molecular biology, and cell biology, and so on. And this has made Kiran Majumdar Shah one of the richest women in India. In addition, like Mahatma Gandhi, she also uh, offered recombinant insulin to the needy for no more than 7 rupees. And right here in Hyderabad, we have a lot of entrepreneurs, particularly uh, Dr. Radha Rangarajan, who started a company. It was a startup company in the University of Hyderabad. And this company was called Vitas Pharma, VITAS Pharma. She has now moved as a lady director of the Central Drug Research Institute in Lucknow. In fact, CSIR now has two or three women as lab directors. One of them there, another one was in Hyderabad, in IICT Hyderabad. And now the Director General of CSIR is a lady. Her name is Dr. Kalai Selvi. We have several more women entrepreneurs and business ladies who started a company. Dr. Anu Acharya is one. She started and runs a genomics company, which is called Genome Patri. Many of us, when we look for brides and bridegrooms and so on, we look at let's look at what Gotra is what Gotra. So rather than do that, I'll also look at your genome and see how acceptable or not acceptable the boy and the girl's genomes are going to be. And so she calls that company as Genome Patri in Biotech Park right here in Hyderabad. And I suggest that IIT Hyderabad also collaborate with companies like Biocon, like Genome Patri, and not too far away from here, in the Indian Immunologicals, on your way from the city to this Gachibowli campus, you will see something called the Indian Immunologicals. And that was started by a lady called Dr. Mahima Datla. Shraddha Goenka is yet another. She got her PhD from CCMB, where she was one of my students actually, and she wanted a startup, and CCMB put together a startup company where they will give you all the lab, they will give you the facilities and so on, and you can start a company, and once you are ready for about 2 years, 3 years or so, you can start up your own company. Shraddha Goenka has one such, and she now has something called biodesk.com. It will be good if IIT Hyderabad also starts a similar startup company so that women in particular can also get going and so on. From what I understand, actually, Professor Kiran Kuchi is apparently is helping out with a startup company. Is that correct? If so, I think there'll be more of this kind. Turn now to women in government and politics. Statistics tells us that nearly half the world's people believe that men make better political and business leaders than women. So there is a clear gender bias about this. And these are more pronounced in both low and high income human development index countries. These biases fall across regions, income, development, and cultures, making the whole thing a global issue. Against this background, let us look at women in government and in politics in India. What about the US? Mr. Donald Trump is the 46th president of US. All the 46 have been men, no woman president. Okay. What about India, the developing nation, which is now clearly developed nation? In fact, Democrats come to power, time a lady president in the US. Here we have the trump card. We had 15 presidents so far. Pratibha Patil was in 2007 to 2012, 5 years as president, and Draupadi Murmu, who is now the current president. But then it's not just India alone. Look at our neighbors. Benazir Bhutto of Pakistan was the Prime Minister of Pakistan, and Sheikh Hasina was the former in Bangladesh. Vidya Devi Bhandari was the second president of Nepal, and Dolma Gyari was the woman president in Tibet between 1991 and 2011. Chandrika Kumaratunga was president of Sri Lanka between 1994 and 2005. If you look at Latin America, whether it is Brazil, Argentina, Chile, or Peru, they had women presidents and prime ministers consistently. Even today, there are 3 of them, 3 countries. Given all this background of women leading the health, wealth, and happiness of the world, let's celebrate Happy Women's Day and Happy Women's Years. Thank you. I'll talk far more about my science when I come here next time. Today, my time is up. Thank you.
Thank you so much, sir, for that insightful talk. Now the floor is open for some question and answers.
There might be very little, I think.
Okay, so if there are no questions, then I would like to welcome Professor C.R. Raj from Broad Area Chemical Engineering, IIT Kharagpur, PMRF Nodal Coordinator, to kindly come up on the stage for felicitating Professor Balasubramaniam.
Thank you.
We now invite you all to explore the poster exhibitions and enjoy some refreshments. This is a great opportunity to reconnect with the presenters and engage in meaningful conversations. We will reconvene at 12:15 p.m. for our next plenary talk. So see you all soon.